right, so in this particular problem, we have two forces. F1 is equal to 10 newtons, and then F2 is equal to 14 newtons. That is applied to a box of 5 kilogram mass. Okay, part A asks us to find the net force, and then part B asks us to find the acceleration in the box. So this is a top view problem, or it is also known as a bird's eye view problem, where you're looking at the system from an aerial view. So you're looking at the top of the box. So therefore the plane is not given to you. So I highly suggest you would just draw a normal coordinate plane because you're looking at top view. There should be a y-axis and there should also be an x-axis. So it's easy to do that. So if one is not drawn for you like I just did, you should definitely draw one for yourself just so you can keep track of what's y and what's x, okay? So it's just pretty straightforward. So as you can see here, F1 is being applied in the negative y direction because the arrow is drawn perfectly straight down. F2 here is drawn where it's being pulled, quote unquote, in the northeast direction, or in this case, the first quadrant because it's pointing right and up. All right. To find net force, all we have to do is apply Pythagorean theorem. So here's this net force square is equal to the net force in the x direction square and the net force in the y direction square. So that resembles a right triangle. So I just made a note here for you if you like, which hopefully makes this stuff easy for you. A Pythagorean theorem is c squared, which is equal to a squared plus b squared. So really the two legs that are being square, and then square root of that will give you the hypotenuse, okay? So that's nothing fancy. So in order to do so, in order to find the net force in the x direction and the net force in the y direction, you should definitely break vectors that are diagonal into its components. Here, the green arrow that just came up, that would be f2x. And f of 2x in this case would be cosine because the dashed green line here along the x-axis relative to this angle that's being given, that is your adjacent. Because it is your adjacent, you would do the hypotenuse times cosine of the angle. Okay, so f2x here is 14 times cosine of 37, and then that should give you a value of 11.18. Well, because it is a diagonal, you also have to have an f2y. So you really essentially you're just trying to find the run and rise of each vector. F2y here is the same process. It is 14 times sine of 37. It's sine because this f2y is the opposite leg of this 37-degree angle, and opposite in geometry is sine. Okay, and if you punch 14 sine 37 on your calculator, you should get a value of 8.43, and that's it. F1 does not have any x component because it is directly down the screen here, which is already perfectly in the y direction. So if we look at the information for the x direction, I only see one vector. In this case, it is f2x. That's pointing right. I don't see any other arrows pointing left. Okay, so the net force in the x direction is pretty straightforward for this one. It is simply one arrow, and that one arrow is f2x pointing right. So therefore, the net force in the x direction is simply 11.18 newtons. However, the net force in the y direction, it's a little more work. So as you notice here, F1 is pointing straight down the y-axis, which is in the negative direction. However, the component of F2y here is pointing upward. Well, you have a arrow pointing upward and you have an arrow pointing downward. So in order to find the net force in the y direction, I will go ahead and write my positive values first. This is 8.43 because it's pulling right and up. So F2y is up, which makes it positive. And then I notice here I subtracted 10. Well, I subtracted because this is negative, okay? Or you can write add negative 10. So it's up to you. Here, I've just chosen to subtract 10. But if you want, you can say add negative 10, which is the same thing. Regardless, the vector pointing down using common sense is 10. The vector pointing up is only 8.43, which is less than 10. So ultimately, the box will be moving down in the y direction, okay? So based on these two values, I know that the box is going to move to the right because fx is positive, but fy is negative, so it's going to move right and down. All right. So if we can translate these values that we got into just a right triangle, because ultimately you're just applying Pythagorean theorem, and to apply Pythagorean theorem, you should have a right triangle. So the arrow that just came up here represents the 11.18. this arrow is pointing in the x direction, so that is my net force in the x direction. So you're just shrinking everything down to just one x arrow, and then you're going to shrink everything down to just one y arrow. And ultimately, you could potentially have a right triangle if it works out that way. Okay, and then this arrow here that just came up, that is my net force in the y direction. But as you can see where my cursor is, my net force in the y direction here is a negative 1.57. Hence, I drew an arrow pointing down, and that arrow is going to be 1.57. Well, if we connect the two dots there, or the two starting point to the ending point, that is your hypotenuse. And your hypotenuse in this case represents the net force. Okay, so it's nothing crazy. You're just doing Pythagorean theorem in terms of physics variable. Well, how do we find net force? We just apply Pythagorean theorem. So now that we have all the values, we can just carry this work down. So therefore, we can say the net force square is equal to the net force in the x direction, which is 11.18. We're going to square that. And then we're going to add. But then you notice here I use parentheses. In parentheses, I'll put negative 1.57 because the net force in the y direction is negative 1.57. And I want to square that. So squaring a negative value is going to give me a positive value. Okay, so it's important that you use parentheses here. All right, so if you do 11.18 square, you will get about 125. And then if you do 1.57 or a negative 1.57, and you're going to square the whole thing. And then a negative times a negative is a positive, so you're going to get 2.46. And then if we sum 125 and 2.46 up, we should get a value of 127.46. Except this is net force square, right? We haven't done the square root yet. So to find net force by itself, sigma f by itself, we take the square root of both sides. So take the radical of both sides. So therefore, net force is equal to the square root of 127.46. And if you do that, you should get a value of 11.29 newtons. However, force is a vector. So you need to include the direction. You cannot say positive or negative for this one because the vector here is pointing in the southeast direction. So therefore, we have to find the angle. The theta that you should reference is touching the horizontal axis here. So from net force touching the 11.18, which is in the x direction. So therefore, to find theta, I think the quickest way to do it for this one, not the only way, I just prefer tangent. Okay, so tangent of theta by definition is rise over run, a y over x. So hence, I have net force in the y direction, which is negative 1.57. I have net force in the x direction, which is 11.18. So I can just plug it in. But to solve for theta, we need to get rid of tan. So really, we just do inverse tan. Okay, so to get rid of tan, we do inverse tan, just the opposite of that. So inverse tan of net force in the y direction over net force in the x direction. So therefore, the net force in the y direction is negative 1.57. And then the net force in the x direction, as we calculated earlier, is 11.18. And then we punch that in our calculator, we should get 8 degrees. So this is 8 degrees in the fourth quadrant. So the proper way to answer it would be 11.29 newtons. 8 degrees below the positive x-axis, or you can say 8 degrees southeast if you choose. Okay, so that's the answer to part A. Part B, asks us to calculate the acceleration in the box. Well, to calculate the acceleration, we would just apply Newton's second law, net force equal to ma. So let's go ahead and get rid of m in order to find A by itself. So therefore, to find A, we take the net force divided by the mass. The net force in this case, we already calculated, which is 11.29, which is this diagonal here. Watch where my cursor is. So that diagonal there has a magnitude of 11.29, okay? Well, 11.29 newtons divided by 5 kilogram. That should give you an acceleration of 2.26 meters per second squared. But you notice here, I also include the direction because it didn't use the word magnitude. So the proper way to express your final answer is 2.26 meters per second squared. 8 degrees southeast or 8 degrees below the positive x-axis. The angle here, or the direction, must be the same as the direction for the net force because net force and acceleration are in the same direction. So if you're pushing right, A has to be right. If you're pushing left, A has to be left. In this case, if you're pushing in a diagonal, A has to be in the same line of motion or direction, okay? So net force and acceleration will always share the same direction. All right, I hope that helps. Stay nerdy, don't be whack.